Hello! In this video, we are going to teach you about nuclear fission and fusion, along with their corresponding nuclear reactors. We've also created animations so you can see how all of our concepts work. We're going to begin with fission and fusion, starting with fusion, which is the simpler of the two. Nuclear fusion is the process by which two or more atoms are combined to produce one or more atomic nuclei. On the reactant side of fusion, you start with two hydrogen atoms being held in place by large amounts of gravity. The two hydrogen isotopes used in fusion are deuterium and tritium. Hydrogen is the lightest element and it is made up of one proton and electron. Deuterium has an extra neutron in its nucleus, and tritium has two extra neutrons, and is therefore 3 times as heavy as hydrogen. In a fusion reaction, the hydrogen atoms are slowly moving closer together, but their electron fields repel each other, which causes the need for such an enormous force to continue pushing the atoms together. If the normal force from the pressure on the hydrogen atoms exceeds the repulsion forces from the electrons, the atoms will collide, as seen in the animation. When they collide, the atoms release energy that had been previously stored in the center of the atoms and fuse together, creating one atomic nuclei. This atomic nuclei is really just a helium atom. In many demonstrations, this is referred to as an alpha particle. The difference between an alpha particle and helium atom is that an alpha particle does not contain electrons, while a helium atom does. They both contain 2 neutrons and 2 protons, and therefore have the same atomic mass. Notice that the only products of fusion are helium and energy.
On the reactant side of the fission reaction, we have a little bit more complicated setup. There is one heavy atom, the most commonly used being uranium-235. To look a little bit more in depth about fission, you have to look at the structure of the nucleus. The number 235 in the name is for the atomic mass of the atom, which is the sum of the protons and the neutrons in the substance. In this isotope, there are over 50% more neutrons than protons. The protons in the nucleus attract the neutrons through polarization. Once there are enough neutrons to spread out the charge of the proton, the nucleus becomes unstable due to energy inside the nucleus that is constantly pushing out. This is why a neutron is needed to trigger fission, because the charge of the proton spreads out over all the neutrons. When there are more neutrons, the charge does not give a force strong enough to hold the atom together anymore. When the extra neutron is added, the force of the attraction by the protons cannot hold the atom together anymore, which causes it to split, releasing energy that is pent up inside, as seen in the animation. As you can see, there are a lot more products left over from the fission than there are from the fusion. Notice the 2 large atoms that broke off. These are called daughter nuclei. They can be any range of sizes. Also, notice the 3 extra neutrons. These are what make the fission a chain reaction. They act as the triggers for fission in more atoms, just like the neutron that started this reaction. This is how atomic bombs work. The first atom that explodes releases 2 or 3 neutrons, which each trigger another atom to explode, repeating until the neutrons are absorbed by an atom that is more stable. Each atom releases a small amount of energy, but with billions of atoms, this becomes a lot of energy. 1 gram of uranium can release the same amount of energy as burning 3 tons of coal. It is also important to note that both fission and fusion reactions release similar amounts of energy, but fission releases a lot more waste.
Now, what about the application of these processes? We can begin by discussing fusion reactors. Fusion reactors are able to harness the immense amounts of energy released by fusion reactions by replicating the process as it occurs in stars. The energy source for all stars is actually nuclear fusion. The pressure in the center of a star is so great that it initiates nuclear fusion by causing 2 hydrogen atoms to fuse and create a helium ion. In a star, the energy from fusion reactions in the center push outwards towards the star's surface to balance the inward pull of gravity. The reactors create an extremely high temperature and high pressure environment, just as the process would occur in a star. In order to accomplish this, 2 different types of reactors have been developed. The first type of reactor is a magnetic confinement reactor. This reactor makes use of intense magnetic and electromagnetic fields that heat and squeeze the hydrogen plasma atoms into fusing with one another. The energy produced is used to heat water and then creates steam that spins a turbine. The second type of reactor is an inertial confinement reactor. This uses powerful lasers to heat the hydrogen fuel to reach the necessary heat and pressure to fuse. The energy released produces steam that spins a turbine. Reactors are capable of producing vast and unprecedented amounts of energy. For example, an ideal fusion reactor would be efficient enough to match the energy produced by burning a barrel of oil using only a single glass of water as fuel. Moreover, it circumvents the environmental repercussions that are associated with fossil fuels and nuclear fission. However, the process is not yet commercially viable for a variety of reasons. Firstly, specific isotopes of hydrogen with extra neutrons are required to carry out the process undergone in the reactor. These are known as deuterium and tritium. While deuterium is easy to access and can be found in seawater, tritium is very sparse on Earth and is radioactive. Additionally, the technology is still largely experimental and currently requires more energy than it produces. This uncertainty makes many reluctant to risk investment into the energy source when many other proven clean energy sources already exist. In sum, only time and continued research will determine the viability of the fusion reactor.
A well-known example of nuclear fission is a nuclear fission reactor. The purpose of a nuclear reactor is to contain and control nuclear fission. Most of the reactors in the world use the isotope uranium-235 for fuel. The isotope is processed in the form of small pellets and is stacked to form what is called a fuel rod. About 200 fuel rods are put together to form a fuel assembly. A conglomerate of assemblies is known as the reactor core, and the reactor core is the fuel that produces energy. The way fission works is that the reactor core is hit by thermal neutrons, slow-moving neutrons with 0.04 volts of energy, produced by the uranium-235 isotope as it decays. These thermal neutrons are absorbed by the uranium-235 isotope to form uranium-236. But the uranium-236 is composed of two fission fragments and releases some extra neutrons. These extra neutrons from the fission process contain enormous energy, 1 megavolts worth. When they bombard into our uranium-135 nuclei, they have a significantly lower chance to start the fission process. In order to start a chain reaction of our uranium-235 nuclei, the reactor core is placed in a coolant/moderator. The coolant slows down the high-energy neutron by having it collide with deuterons, ionized deuterium, found when separating natural heavy water from natural water, with only 1 proton and 1 neutron. The neutron gradually loses its energy and becomes a thermal neutron. It then starts a chain reaction with other uranium-235 nuclei, producing more energy. In reactors, water or heavy water is commonly used as a coolant. In addition to coolant, control rods are also a key component of nuclear fission reactors. The purpose of a control rod is to control the output of energy within the reactor. It does this by absorbing the extra neutrons within the reactor, limiting the amount of reactions that can be used to produce energy. They can be taken in and out of the reactor, and the reactor can work without them. They are often made of boron or cadmium, as they are both materials that absorb neutrons. During the fission process, some of the mass is converted into energy as well. This energy is the heat energy that is produced and then directed to an extra source of water, which is soon turned into steam. The steam produced turns to huge turbines of electric generators, producing electricity. Even though nuclear reactors are not supposed to produce any waste, nuclear waste is produced as a byproduct of the fission process. During fission, some of the uranium-235 isotopes in the pellets are turned into cesium-137 and strontium-90, or fused with extra neutrons to form plutonium-239. These isotopes are all radioactive and have half-lives of 30 years to 24,000 years. They are put into spent fuel pools to contain the radiation. There is also low-level waste, which are things such as clothes of workers that have been exposed to radiation.